Okay, let's get started. First of all, are there any questions about anything, homework-wise, breadth first search-wise, depth first search-wise? Before we get started, homework-wise? Okay, in case I don't remember to mention it later, I gather some of you are aware you have a fall break coming up. Okay, so that's, we will not have class on Tuesday. It's an excellent time to go and work on the graph algorithm homework questions, okay, to read the book on breadth first search and depth first search, and thoroughly enjoy your break. Any questions about that? Okay, if so, let's get started back to this idea of depth first search. So where were we? Last class we had just introduced the idea of topological sorting, which is a important idea on directed acyclic graphs, okay? What I wanted to do before I talk to you a little, show you a couple of implementations of algorithms that find topological sorts of directed graphs. I want to show you something about depth first search that I didn't talk about before. That if you took a look at the code carefully, you may have noticed that while I didn't talk about it, there are these funny things having to do with time. Okay? That there's a time when that I set whether or not something is, that the moment I discover that V is true, I increment the clock, T, and I say that the entry time to V was at this time. What am I going to do? I'm going to claim that for every vertex, there are two events that are interesting in its life in a depth first search. One is when it's discovered, because the moment that we discover a new vertex, we suspend everything we're doing and focus our search then. The other time that is interesting in a depth first search is at the end. Once we have finished processing it, we're going to exit, okay? And there's kind of an entry time for every vertex and an exit time. And that's what this clock is keeping track of, okay? You can kind of think a little bit about what happens. What are the entry and exit times of vertices, if you think about it? Let's see if I could reconstruct it on the example we did. And there's a reason why I'm going to mention it. Here was our example. What was kind of the entry time? If I look at this depth first search example, what is it that kind of happened? I think the entry time for this vertex was 1. Then it discovered another vertex. That was the second event. It discovered a third vertex. That happened at time 3, time 4, time 5, time 6. When we were searching 6, there was nothing else to do, right? We finished up with 6. 6 was the first vertex we were finished with. This had an exit time of 7. Then we recurred back to 5. Once we checked out all of 5 things, nothing else happened. The exit time for this one was 8. 9. The exit time for 3 was 10. The exit time for 2, well, we didn't exit 2. We used it at time 11, we discovered 7. And at time 12, that ended. At time 13, if I am correct by this model, we finished with 2. Then, at time 14, we discovered 8. At time 15, we ended 8. And at time 16, we finished with 1. Do people get an idea of what the clocks are here that I'm talking about? Okay, so what's interesting about these clock things? You can think of that as the lifespan of a vertex. Are there any observations to be had? It's clear that the guys at the top have longer lifespans than the guys on the bottom, right? In particular, your parent was born earlier than you, and in this world died, finished later than you. Because the parent's job wasn't finished until the child had completely finished. Does everybody kind of get that idea? And so every vertex kind of has a start time and a finishing time. Okay, does everybody kind of see how we can do that and how we can maintain that very, very easily by just incrementing this clock? Okay, any questions? Yes? Where would I apply something like that? I might apply that in topological sort, okay, which is why I'm now mentioning this. Okay, so ask that question if I don't answer it again in a couple minutes. Okay, fine. Actually, let's think about this as a directed graph and maybe answer it right now. Suppose we have a directed graph, a directed acyclic graph, where we have a vertex, V, and it discovers a vertex, Y. Let's call it Y. And Y is going to have some directed edges coming out of it and stuff like that. If it's a directed acyclic graph, what did we know? We knew every edge. Okay, what do we know? The fact that there is this edge from V to Y means that if we were doing a search starting from the V was going to finish later than Y. Let me say that again because it's maybe not obvious. I'll probably say it with different variable names this time. Suppose we have a directed acyclic graph, and suppose we do a depth first search of it. Now the edges are directed. Now there are no cycles, right? If I start doing a depth first search from up here, and at one point there's an edge xy where Y gets discovered, what do we know about this? The finishing time, Y is going to now be done, there's going to be a search done from Y, and only after Y is finished will the search get back to X for X to finish. Does everybody agree that the finishing time of X is going to be greater than the finishing time of Y? Okay? But X has to be before Y in the topological order. If you believe that, then actually if you take the vertices and you sort them by finishing time, that is enough to topologically sort the vertices. Okay? That kind of, if you finish before me, okay, I had to be before you in a topological sort. Okay? And that basically is an argument that a simple topological sort algorithm is simply sort the vertices by their finishing time. Okay? Any questions about that? So there's certain algorithms for which knowing about the finishing time matters. It's also the case that it makes certain edge classification things easier. Okay? But I think that's the compelling argument I wanted to give you. Any questions? Okay? So let's go back to topological sort before I talk about the problem. In fact, if you take a look at it, again, you didn't quite see this. When I'm trying to test whether or not what type of an edge, remember when we have it do any traversal of any graph, edges could be, remember we saw that there were 4 types of edges. You could have a forward edge, you could have a backward edge, you could have a cross edge, you could have, if it's a directed acyclic, if it's a directed graph, you could have forward edges. Okay? If there was an edge from what was my root to something else, if I started doing a DFS, I could have gone bunk, 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 and only when I had finished processing this vertex and this vertex and this vertex, then I might get around to seeing that edge. So I could have forward edges in directed acyclic graphs, in directed graphs. I can have cross edges in directed graphs, okay? But it's often interesting to know what type of edge I have. And the argument here is that there's, how can I look during a traversal and tell you what type of edge I have? Okay? The simplest algorithms that I found kept track of when did we enter each vertex, okay? And that helped make that decision of separating what's a forward edge from a cross edge and so on. Okay, I don't want to go through the details, but you can kind of believe that. Any questions? Okay, where is the relevance that I want us to go to? I want us to take a look at that topological sort algorithm again. Topological sort is the mother of all directed acyclic graph problems. If you have a directed acyclic graph, you are going to want to topologically sort it. Just like if you have a bunch of different numbers, you're almost certainly going to want to sort them. Okay? It's kind of just a default thing. Let's remind ourselves one more time about what the topological sort did. The topological sort was an ordering, where all the vertices, you ordered them from left to right, such that all edges went from left to right. Okay? That's what a topological ordering is. And any edge ij is therefore a vote that I has to be to the left of j. Okay? And a topological sort is how you laid it out to come up with such a systematic order. Any questions? So how can we find topological sort? Okay? Well, there's two different algorithms that I'm going to present, both because both are fairly easy. The one that is the prettiest one is the one that just uses depth first search. Okay? As this gentleman just learned, okay, if I sort the vertices according to their finishing times, where the last to finish was the first to, to go, okay, well, then that means I can do a topological sort by just doing a depth first search. Now, depth first search on a directed graph is more complicated looking and more complicated to think about than on an undirected graph. We love depth first search on an undirected graph because every edge was either a tree edge or a back edge. That was what made depth first search great. On a directed graph, the labeling is much more complicated. Okay? But again, there's still very many useful things you can do with it. One thing I showed you was you could identify directed cycles using depth first search, right? If there was a cycle in a directed graph, by just doing the search, the moment you had a back edge, that meant that you had a cycle. Basically, labeling the vertices in reverse order of when they were marked processed, which is exactly the finishing time, gives you a way to, topologically sort the DAG. Now, why is it? Suppose if we did a depth first search and we encounter a directed edge xy. Every edge in the graph is going to be seen in the course of a a depth first search. We're going to see if it was an undirected graph, we'd see each edge twice. If it's a directed edge, we're going to see it once. We know we're going to see it. What happens when we see the edge? Okay, to give you an idea of why that finishing algorithm is correct. The first case is pretty much what I talked about before. Suppose there was an edge xy. Okay, we need x has to be before y in the final order. if y was undiscovered when we processed x, then edge xy is going to be a tree edge. We're going to start a depth first search from here. The finishing time of this is going to be after the finishing time of that. And y is going to appear to the right of x just like it has to because of the edge. So that is good. What if we had an edge, xy, where y was discovered but not yet completed? Remember kind of how things proceed in a depth first search. Okay? Originally things are undiscovered. Then we mark it discovered but not completed. When we discover something else, discovered, discovered. It's only after we have finished working out all of its stuff that we mark an edge completed. What if we have an edge from one, we're working on, we're expanding a vertex that's been discovered. What if we have an edge back to another discovered vertex? Well, that discovered vertex, to be discovered but not completed, means that you're an ancestor. And if you have a back edge, that's going to create a cycle. If you have a bunch of tree edges going down and a back edge, that creates a directed cycle. If the graph was a DAG, you didn't have any cycles. So this case can't actually happen. The other possibility is that y goes to a completed vertex. Okay, how could that have happened? Well, let's imagine a world where we have a DAG that looks like this. Does everybody see what I've got? I've got one vertex, two vertex, three vertices, four vertices. If I start doing a search from this, okay, this is, what you call it? If I start doing a search from here, it's discover, discover, complete, because there's no outgoing edges from here. Complete, complete. Here was another vertex that wasn't reachable from the root. If we start our search now from here, remember, just like with connected components, we're going to go through all the vertices of the graph. If this vertex was still undiscovered, when we do a search like that, this means that this vertex has to be to the left of that vertex. Well, what does that mean? That's this is what the case is over here. And in which case, this one will have been completed before this one. Okay? And likewise, that means that this one can be to the right of the topological order. Okay? And this one will be to the left. This one will go before any of the other vertices in that component. Okay? Any questions about that? So if you buy this reasoning, then keeping the vertices sorted by completion time is a way to topologically sort the vertices. You wouldn't want to actually sort the numbers. There's a slicker way to maintain that. This, I claim, is my topological sort thing. What am I going to do? In any depth first search algorithm, you want to add things to, basically when you visit a vertex or when you visit an edge, okay? What do we do when we encounter an edge? Everything's going to be fine so long as we don't have any back edges. If we have a back edge, it's trouble. So when we see an edge, we'd better make sure it's not a back edge. Okay? What are we going to do on a vertex? Well, the moment a vertex is processed, which is going to happen at process late, we're going to push that vertex on a stack. And now then, the order of the vertices on the stack is going to be the vertices in the order of when they got completed. Okay? And from that we can read off a topological sort. Any questions about that? When everything works out, the algorithms using depth first search are amazingly concise. Okay? Basically, just do something at each vertex or edge, and that's the case with depth first search, with topological sort. Any questions? Okay, good. One more. Boom. Let me show you one other way to do topological sort. And again, basically, this was the algorithm. Again, before, it was that we were going to call depth first search. Okay? Basically, but we're going to go through every vertex on the one by one. If it hadn't been discovered, we're going to do a depth first search from it. This is what we did with connected components. This makes sure we're eventually going to search from every vertex in the directed graph. Okay, even if it's not connected, even if it's not strongly connected, we'll talk about what that means later. And then basically printing out the stack in the order, once you have them sorted by finishing times, printing them out, what's on the stack in the right order gives you the topological sort. Any questions? Okay. Now, the other idea for topological sorting I hinted at last class was to observe that if you have a vertex of in degree 0, it may have a lot of out degree. If you have a vertex of in degree 0, you can put it first in topological sort, and it's not going to make any problems, right? We're concerned about having an ordering where vertices go from left to right. If nothing goes into this vertex, there's no reason why it can't start. Does everybody kind of agree? So what are we going to do? We're going to find out which vertices have degree 0, in degree 0. Then we're going to take one of them, put it first, delete the edges going out of it. In that process, we might take more vertices of in degree 0. We might create more vertices of in degree 0. The ones that are in degree 0, we're going to put on our data structure and then pull them off basically in order of now in degree 0. Okay? So the one that's in degree 0 goes first. Deleting it is going to create other in degree 0 vertices possibly, deleting the outgoing edges from it. Okay? At every step we take a vertex of in degree 0 and put that next. Any questions? Why must there be, for any DEG, a vertex of in degree 0? Yeah? Otherwise there'd be a cycle. Well, if there is a cycle, it's clear that none of these vertices can have in degree 0, right? It should be here that for any graph that can be topologically sorted, at least one vertex has to have in degree 0, namely the one that we're putting first, right? So anything that can be topologically sorted has to have a vertex of in degree 0. And it turns out any DAG can be topologically sorted. Any questions? Okay, so how do you do, I want you to look at this just as an example of a non-depth first search way to program graph algorithms. Okay? Just to make sure you understand the bookkeeping that's kind of involved here in dealing with adjacency lists and things like that. What is my situation going to be? I am going to be topological sort in this way. I'm going to keep track of the in degree of every vertex. I'm going to have a queue that keeps track of all the vertices of in degree 0. What am I going to do? First, compute the in degrees of every vertex. How many edges go into each vertex? Now is this easy or hard? Let's think about it. If we have a DAG, how do you compute the in-degree of a vertex? Okay. How do you compute the out-degree of a vertex if you have an adjacency list representation? What's the out-degree of a vertex? Yeah? You go through its row, and it's what the list is, right? It's the length of that list. What's the in-degree of a vertex in a directed graph? Well, it's not clear where this is sitting, right? This is kind of spread over all the lists, right? All the lists could point back to me. So how am I going to compute the in-degrees of each vertex? I am going to, in linear time, walk over each vertex and do this. What am I going to do? I'm going to build an array that is the in-degrees. Initially, every vertex is in-degree 0. I'm now going to walk over each one of the n adjacency lists. And suppose I discover an entry j on i's entry list. If I look on i's adjacency list, I see an entry j. Whose in-degree does that add to? What? J, right. So if I have an entry j on i's list, okay, that means the in-degree of j has gone up by 1, right? So what am I going to do? For I goes from 1 to the number of vertices. For each edge on i's list, if I have if I have an entry p sub y, I'm going to increment the count, the in-degree of the count of p of y. That's going to be this vertex. And then I'm going to finish cruising through this list, bop, 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 and then go down to the next one. What is the running time to compute this vector of all the in-degrees? If I have a graph on a directed graph on n vertices and m edges, how much time does this take to compute the in-degree of every vertex and edge? O of m? N plus m. What if there were no constraints? What if there were no edges? What would this algorithm take? If the graph was so sparse as to have no edges, this loop would never go around, right? But this loop is still going to go around n times. So I'm going to say order n plus m. Usually m is bigger than n, the number of edges. In most interesting graphs, the number of edges is bigger than the number of vertices, certainly in a connected graph. But if you have a very, very sparse disconnected graph, maybe it's not. That's why I say it is n plus m. Any questions? Do people see now how I compute the in-degrees of every vertex? And it turns out that to compute the in-degree of any one vertex would cost as much as to compute the in-degree of all the vertices. So I might as well compute that vector right now. Any questions? Oh, sorry. That's you. Okay. What else did I have to do? Well, what's my thing going to do? Basically, I've computed the in-degree of every vertex. What am I now going to do? My queue of things that are of degree 0 is initialized. And I'm going to go through all my vertices and find which ones have in-degree 0. If it is, I enqueue it onto my to-do queue. How much time does this part of the code take? Once I have the in-degrees, how much time does that take? How much? O of n, right? So this was n plus m. This was n. Now what am I going to do? Let's get rid of that part. Now, what is good about this? Now, while my Q is not empty, what am I going to do? I'm going to pull out a vertex of degree 0 and put it next in sorted order, my topological sort. If it's in degree 0, I can put it next. Then what am I going to do? I'm going to go through all the outgoing edges. Once I've decided to put X someplace. There are no ingoing edges to me, but there might be outgoing edges. For each outgoing edge, if I have an edge to Y, what am I going to do? Once you put me in and I want to delete these edges, what happens when I delete that edge? Yeah? The in degree goes down by 1. That's exactly right. So for each edge, I'm going to decrement its degree, okay? And if the degree is equal to 0, now I care about it. Now it's a potential next vertex, right? And I'm going to stick it on the Q. Does everybody see what I'm doing here? What's the running time of, what's the running time, of this part? I've got a while loop within a while loop. What is the running time of this? Let's think about it. What's the running time? How many times is the outer loop going to go off? How many times? N. How many times is this while loop? I guess the while loop, the while loop went down to here. Right? How many times is this while loop going to go around? M. I claim in each iteration, it's going to go through according to the degree, the out degree of V, right? This is the degree of V, right? Now, what's that mean? The sum over all n loops. What's the sum of how many times this is going to go around after all n vertices? How much is that? Okay, it's the out degree of vertex 1 plus the out degree of vertex 2 plus the out degree of vertex 3, ... What's that going to be? M. So the total time is going to be n plus m. Okay, any questions? Do people see how I implemented this one? This is a good one to see for just general mechanics of working with adjacency lists and how we manage to make an algorithm that runs in linear time, keeping track of the counts of every vertices in degrees as we did all those deletions. Okay? So this one I find an algorithm easy to think about. But if you take a look at it, the depth first search way was wildly easier to program once you had depth first search. But you had to understand this connection between finishing times and topological sorts. Any questions about that? Okay. Maybe I'm going to do one more thing. I'm going to save this. I'm going to come back to the daily problem now. Let's just think about the, yes, question. The n comes from, you could say, the code in each iteration of the loop, right? That there's an outer loop that goes around n times. But what if I didn't have any code in that? Let's say, what's the running time of this algorithm? do nothing. Is this still O of n? It's still going to loop around n times. It's going to increment. I is going to go 1, 2, 3, 4, 5. So it didn't depend on me having a statement in here. The loop itself would have gone around n times, right? Unless you had a super smart compiler or something like that, that made that go away. Okay? But that's where the n came from. Any questions? Okay. What was the problem of the day? You are teaching a class of n rambunctious kids. You have to want to march them in a line. You have inside dope that certain kids hate certain other kids. They hate them enough that if I got into a situation where I was in a line and that kid that I hated was ahead of me, I would try to throw a rock to scale him on the head. Does everybody get that idea? How can I order the kids? So if I'm given information about I hates J, how can I order the list so that, if I hates J, I want J behind me. Okay, I. Any idea? What kind of problem is this? Yeah? It's clearly a topological sort thing. How do we get into trouble in our school? Is if Joe hates Mary, and Mary hates Bill, and Bill hates Joe, then they got problems, right? This is exactly a topological sort. Okay? And so topologically sorting it and putting it in either, maybe the reverse of the topological sort. If my line's going this way, I want all hatreds to go over from that side to this side. Any questions? The second part of the problem is more interesting, though. What if, notice that if I have a class of 100 kids, if I arrange them in a line of 100, that seems complicated, right? How would I find the shortest order of this so that all the hatreds go in one direction? Okay, do you see what's kind of happening? In a let's say we had a world where these two vertices were not connected to anybody, right? Well, let's say they were. This guy's connected to there, this guy's connected to there, and maybe this guy's connected to there. Okay? Suppose we wanted to arrange the vertices in ranks such that we minimize the length and all the edges go from left to right. They don't have any within, you can't have an edge like that. But does everybody kind of see what I want to do now? I want a topological sort into kind of platoons, okay? Such that all edges go from left to right while minimizing the number of platoons. Can anybody give me an idea how I would do this? Yeah?
You could get all of the nodes in degree 0 and act like that's your first node. And then
Notice that there were multiple in degree 0 nodes, right? And there's no reason why all of them couldn't be first, right? So what am I going to do now? I'm going to put all the in degree 0 nodes first. Then I will delete all outgoing edges of all of these guys, right? And any one that is of in degree 0 now can go in the next rank. Okay? Any questions about that? Should be clear that I'm not going to get any benefit by taking the in degree 0 nodes and spreading them into two groups. Okay? So that would be the way that I could represent this class, keep the line short while making sure nobody gets hurt with a rock. Any questions about that? Okay, good. One last thing that I would like to talk to about directed graphs before I get on to kind of a different topic. There is another directed graph problem that you should know about that can be solved by depth first search The algorithm is in the book. I'm not going to go through details of the algorithm. But I find that with graph algorithms, it's very, very useful to know what the problems are. If you know what the classic problems are, it's amazing how often when somebody comes to you with an application, it really turns out that your problem has a name, and it's a classical graph algorithm problem. Now, one problem that is important is finding strongly connected components of a graph. What is a strongly connected component of a graph? A strongly connected component is one where there exists a directed path between any two nodes. Now, when we talked about connected components of undirected graphs, remember we had this idea that here was the United States, and here was Europe, and the road networks were separate components, right? And we saw how to find that in an undirected graph world, right? You just started a depth first search from here, discovered what could be discovered. Anything in a undirected graph component you could discover from doing a search, okay? And that was how you found connected components in an undirected graph. Now notice that it's a little more complicated if we have a directed graph. Let's say we have a ka-chunk, 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 ka-chunk. What is this saying? Here I've got a cycle of 3 vertices, right? From here I can go to here, 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 here. That's clearly strongly connected. I can drive between every piece. Here I can drive from here, chunk, 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 right? But what happens if I start over here and drive this way? Is there any way for me to get home? Absolutely not. You have to sell your car because there's no way to legally drive back to where you started from, right? So the notion of what connected means for a directed graph is more complicated than for an undirected graph. In fact, just about everything in life is more complicated for a directed graph than an undirected graph. We say that a graph is strongly connected. A part of a graph is strongly connected if all the vertices, okay, between any pair of vertices, there's a directed way to get from I to J. The strongly connected components of a graph are the chunks of the graph, such that within each chunk, you can get, you can get between every 2 places. And but there might exist, one-way directed paths between chunks, like we have here. Okay, so the strongly connected components problem is given a graph, break it into strongly connected pieces. Any questions about that? Can anybody come up with an idea of how you would find strongly connected pieces? Let's not worry about the speed exactly. But suppose I had a directed graph. I wanted to break it into strongly connected pieces. What looks like the kind of most important thing there? Any ideas? Yeah? Finding a cycle. A cycle is a great thing. If I find a directed cycle in a graph, what do I know about the strongly connected component? Every one of those vertices on that cycle is in a strongly connected component. You have a racetrack around it, right? Does everybody see that? What about if I now have a separate vertex? Let me do this. another vertex, another path that goes around from two vertices in my cycle. Does everybody see that if I have a directed cycle here, and I have a path from one vertex in the cycle to some other through some vertices that aren't in there, back to the cycle, these guys are also part of the same strongly connected component, right? So with this kind of idea, it should be clear that, well, you could use depth first search to find a cycle. Then once you have a cycle, you can kind of shrink that cycle into a single node and ask if there are other cycles involving that vertex. Okay? And if you repeatedly did this with depth first search, it should be clear that you could probably find all these components in something like n depth first searches. It turns out if you're very clever, or you read my book, okay, there's a way to do it in actually only 2 different depth first searches. Okay, but it requires something kind of clever. For now, what's the important point? Your goal should be to understand what a strongly connected component is. For this DAG, there were 3 strongly connected components, red, blue, and green. And the structure of them basically was, we found a cycle. In this case, my directed cycle was, let's say, ka-chunk, ka-chunk, ka-chunk. And then I added it with a path on there, and that's what made that component. This vertex, I found the cycle, ka-chunk, ka-chunk, ka-chunk. And then there was an edge from this component down, from this component to another separate vertex, and that one down. Okay, so I kind of end up with a bunch of components and a DAG, a non-acyclic graph between them. Okay? Bottom line, you should know about what strongly connected components are. See that it's a natural thing to want to do on a directed graph. Okay? And and recognize it if you need to. Any questions? Suppose I've got a DAG on n vertices. If it was a DAG on n vertices and m edges, how many strongly connected components are there on an n vertex DAG? It's a DAG. Yeah? 0? It's not 0. Is a vertex by itself? Can I get between any pair of vertices in that component? Can I get from me to me? Yeah. So an isolated vertex would be its own strongly connected component. That's what happened here if you look at it, right? So how many strongly connected components would a DAG have? N. One for every vertex would be in its own component, because you can't get away from that vertex and get back to it legally. That's what it means to be a DAG. It's got no cycles. Okay? So that's kind of, again, the structure of strong components and cycles kind of means everything. Okay, any questions about depth first search, breadth first search, DAGs, directed graphs, anything like that? If not, then I'm going to change gears here. Any questions? Okay. So we've seen there's this world of breadth first search and depth first search, and surprisingly efficient graph algorithms for certain problems. Okay? There is another world of optimization problems that are related to things on weighted graphs, particularly edge-weighted graphs. Okay? If you wanted to find the shortest path in a road network, roads have different lengths, okay? And we saw breadth-first search would find the shortest path between two nodes in terms of the number of hops. But if certain hops were longer than other hops, okay, we were in a weighted graph world and not an unweighted graph world. So from now on, actually from now for the next several classes, we are going to live in a weighted graph world. There's a universe of problems which assume that every edge has a weight. And if you looked at my adjacency list representation very carefully, certainly what we cared about was that every edge in the adjacency list, every node that we had, it had to have the identity of the vertex that it represented, and it needed a pointer to the next one. That was this field and this field. If we add another field to every node with the weight, we can represent, using an adjacency list, edge-weighted graphs. Every node of the adjacency list contains a, now there are three fields. There is what vertex is represented by this, what's its weight, and what's the pointer to the next thing. Any questions about it? So edge-weighted graphs fit very comfortably into our world of adjacency lists. Any questions about that? How would we represent a node-weighted graph? Let's just think about it. Suppose the weights were associated with every node in the graph. Okay? Let's imagine a Facebook graph where people were friends with other people, but Facebook knew how much each person weighed. Okay? Maybe they wanted to keep track of this. Where would you keep that information? In an adjacency list type thing. Yeah? The Y value? Well, this is the representation for each edge. If we look, remember, at what our adjacency list was. Remember we had it as being an array of linked lists? Each vertex had a linked list. What if we keep track of the other fields for each vertex by basically being an array, okay, of each vertex? Here I'm keeping the degree of each vertex, right? I would keep the degree as being another field that's parallel to that. I could keep the weight of a vertex as being basically defined in an array. So when I look up each node I can find its weight. Okay? Any questions? That said, we're not going to worry about vertex-weighted graphs. We're going to worry about edge-weighted graphs, because those are the ones that have more interesting problems associated with them. Okay? Any questions? Okay. So what is the mother of all weighted graph problems? It is a famous problem called minimum spanning tree. And the minimum spanning tree, we know that for a graph, if it's connected, if it's an undirected graph, which is what we're going to be dealing with now, okay, a tree is a connected graph with no cycles. A spanning tree of a graph is a subset of the edges such that every vertex is in our subset and the connections there are a tree. Okay? So we could imagine a world where here we got let's call this an unweighted graph. A spanning tree is going to be a subset of edges that form a tree. That's good. I like that one. I like this one. I like this one. I like this one. That's nice. Does everybody see that those red edges are a spanning tree of a graph? Okay? The graph was connected. I claim every connected graph has at least one spanning tree. Okay? If it's a tree, it's a spanning tree. Otherwise, if we delete edges that leave a tree, what's left is going to be a spanning tree. Any questions? Let's see if you're on the ball. How can you construct a spanning tree of an unweighted graph? If I want you to build a spanning tree of an unweighted graph, undirected, unweighted graph, how would you build a spanning tree? Yeah? You could start from some vertex and do a DFS. Notice the parent relation. The tree of discovery is a spanning tree, right? What if you want to do it without BFS? What would be a way to do it? You do it with DFS, right? Both BFS or DFS. The tree of discovery is going to be a spanning tree. Okay? So finding a spanning tree of a graph is not rocket science. What becomes interesting, though, how many different spanning trees can a graph have? What graph on n vertices has the fewest spanning trees? Can someone give me a graph on n vertices that has the fewest possible spanning trees? What? If it was just a path, ka-chunk, 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 in fact, it's already a spanning tree. It's already a spanning tree, right? If the graph is a tree, and notice it didn't have to be a line. If the graph was a tree, there were only one spanning tree. Does everybody agree with that? What graph on n vertices has the most spanning trees? Yeah? The what? Fully connected graph. Ka-chunk, ka-chunk, ka-chunk. Does everybody believe that a complete graph, there's the most possible number of ways of deleting edges to get a spanning tree? How many spanning trees are there? It turns out, if I'm showing off, there are n to the n minus 2. But the answer is a lot. Okay? Any questions? There's so many of these things that if we want to find a single best spanning tree, we'd better not be going through each tree one by one, or else it's going to take exponential time. Any questions? Okay, good. Now, what is a minimum spanning tree? A minimum spanning tree of a weighted graph is the one where the edges sum up to minimum weight. Okay? And again, if all the edges had weight 1, that would be a weighted graph. And any spanning tree of an edge of that graph would have n minus 1 total weight. So you can have ties. But when we want to find the minimum spanning tree, we want a tree whose edges sum to minimum weight. Any questions? Let's imagine, let's cross this off. Let's imagine a weighted graph where we have a complete weighted graph, where we have these points, and they're connected, and the weight of an edge is the distance separating the 2 points. Okay? Imagine a complete graph here where every one of these points is connected to every other one, and the weight is the distance. Which of these is the minimum spanning tree? Which one is cheaper? Do we agree these are two different trees? They're both spanning trees of that complete graph. Which one of these is going to be cheaper? Okay, have smaller cost. Is it the one on the left or the red one or the blue one? Yeah? You think the red one. Well, one way to think about it is this thing is going to be one radius plus the circumference of the circle, right? This is going to be n radiuses, right? And by the time n, since the circumference of a circle is what? It's something like pi times r, if I remember correctly. Okay, by the time you got 4 or 5 points here, this is going to be much shorter than that. Any questions? So this is the one that is the minimum spanning tree. This is another kind of tree. On the example here below, do you see how we have this graph here? Let's say the distance of the, again, I find it's easy to represent weighted graphs if you say the weights were their Euclidean distance. On the picture below, the gray edges and the red edges are the input graph. The red edges are the minimum spanning tree of that graph. Any questions? Now, why on earth would we want to compute a minimum spanning tree? Okay? Well, certainly, I'll tell you why we want to talk about it. Okay? One thing is that there's a bunch of reasons why why it comes up, and I'll show you that in a minute. Another reason why I'd like to talk about it is just like sorting, there are many different algorithms for it. Okay? And just like sorting, in order to make it run fast, you got to be clever. So there's some ideas behind finding minimum spanning trees, getting the data structures right that are worth talking about. But the other thing that makes a minimum spanning tree kind of an amazing problem is that it turns out to be one of the rare problems where the greedy algorithm gives you the right answer. What is the greedy algorithm? Let's say you want to find the globally best thing. One way to build, like when we were thinking about it the very first class, we were talking about this robot tour problem. And everybody said, how do we find the best store? Well, start from one point and find the next point that's closest, the next point that's closest, the next point that's closest. That's what we mean by a greedy algorithm. You're making a local decision now of your possibilities and taking the best thing to do. Okay? You know, if I want to make a lot of money, what is the way I can make the most money in my life? Well, one possibility is if you're right here, stick up the guy with the biggest wallet in the class, and then rob the next guy with the biggest wallet. That might be a greedy kind of an algorithm, right? Much better, of course, would be to instead not make any money at first, do well on your classes, and then get a good high-paying job in computer science, right? So greedy algorithms sometimes give you the best way of doing things, but usually they don't. Remember back to the TSP problem we talked about the first day of class. That greedy algorithm, even though you locally took the cheapest edge, you didn't end up with the best possible Tor. The amazing thing about minimum spanning tree is those kind of algorithms work. And we're going to want to see why that works. I think that's an important thing to see here. Okay? So this is why we talk a lot about minimum spanning trees. But let me give you some kind of ideas why finding the minimum spanning tree is a useful thing. Suppose you work for the cable television company. Okay? And you have a bunch of houses, and you want to connect them to get cable. What do you want to do? You have to dig wire under the ground to connect the houses, right? One possibility is to connect the houses like this. See, they're all going to be connected. Is this great? Why would a cable, what's going to be the problem? Well, among other things, when you're digging the wires under the ground, you pay for the length, the amount of you pay is proportional to how long each wire is, right? What would the cable company prefer to do? It would prefer to find a, nice, cheap way to connect all the houses. Maybe something like this, okay? And so there you would want to find a way to connect all the different sites, okay? So that use the minimum amount of wire. Does everybody kind of see this? A lot of the original work on minimum spanning tree was done by the telephone company, because that's naturally what they had it to do. Any questions about that? You should see that that is a minimum spanning tree problem. Let me tell you about another minimum spanning tree-like problem that comes up in analyzing data a lot. I teach a data science class at the graduate level.
So it's usually...
And one thing that you often want to do is to cluster data, to see when there's patterns in the data. Now, how many clusters of points do you see? How many clusters? 4. How would you teach a computer to try to find how many clusters there are? This seems like a natural thing to want to do. How could you do this? Well, what if you had a graph that was initially complete and it knew the distance between, where the cost was the distance between each pair of points? What would the minimum spanning tree of these points look like? I'm going to claim they're going to look something like this. Ka-chunk, ka-chunk, ka-chunk. Does everybody agree that that's kind of what the minimum spanning tree would be? Now, what happens if we delete the big edges? Does everybody see that finding the minimum spanning tree of these points and deleting the big edges gives us some hope of retrieving the clusters? Okay? So a lot of clustering problems reduce to finding minimum spanning trees. Okay? Any questions about that? So these are good reasons why minimum spanning tree is an important problem. Okay? And I assure you that there are others. In fact, I even, again, if you read one of my war stories, one of these clustering problems came up to minimizing the testing time on that robot that I talked about earlier. And there's other ideas of where minimum spanning trees come up. But you should be able to understand why minimum spanning trees come up and why they are a natural problem. In fact, I will tell you that right now that often after you graduate, sometimes I run into old students and they come up and introduce me. Yeah, I took your class. I took your algorithms class. I learned about Prim's algorithm. I learned about Kruskal's algorithm. And I then ask them, well, what does it compute? And then they don't remember that it's a minimum spanning tree. And these people slink away in shame. So this is the question I will ask you if you find me in a later time. So it's important that you come to understand what a minimum spanning tree is. Any questions? Okay. Let's now go through an algorithm for finding minimum spanning tree. And the thing that's interesting about minimum spanning tree algorithms is that they are basically simple, but they require a proof of correctness, which is non-trivial, but one you're supposed to understand. So this is going to be a world where I'm going to care eventually about the proof of correctness I'm going to want you to understand. What is the idea of Prim's algorithm? We're going to start on some vertex, And we're going to try to do something greedy. We're going to take the cheapest edge that will grow the tree by 1 without creating a cycle. Does everybody agree that we can now go to another vertex? We can go to another vertex. If we take an edge that connects a vertex to a vertex that's already in the tree, then we're dead. That creates a cycle. Does everybody see that? This is bad. So we have to make sure that we're going to take the cheapest edge, wherever that edge is, and not create a cycle. Okay? What is an example of that? Let me just go through and show you now what Prim's algorithm does to make sure you come and understand it. Okay? Here we have our graph. Here we're going to start on from vertex A, and we're going to keep adding the cheapest edge that will grow our tree without creating a cycle. What is the cheapest weight edge that we can add starting from where we are to create a tree, to grow a tree that doesn't create a cycle? What's the weight of that edge? 5. What is the cheapest edge we can add now that will grow our tree without creating a cycle? 7. Which 7? Are we better off taking the first one, or are we better off taking the second? Doesn't matter. Can we take both? Well, in this case we could actually we couldn't take both, it turns out. Okay? Which one did you want to take? Let's say I want to take the bottom one. Now, what is the next smallest edge here that I can take to grow my tree? What is it? I see some people are saying 4. Those are people who don't have very good eyes. Does everybody see that this is a 3? Okay? What is the next cheapest thing I can grow? A 2. Which 2 do I want? Maybe I'll take this one. What is the cheapest thing that I can grow, cheapest edge I can now take that will grow my tree? 2. What is the cheapest edge that will now grow my tree? 4. Can I take this edge of 4? No, why not? It's going to create a cycle, right? But if I take this, does everybody agree that that's done? Okay? And what was the weight of that thing? The weight of that thing was what? I see 4 plus this, that's 12, 16, 19. 19 plus 4 is 23. That was going to be 23, 25, 27. Does everybody agree that that's going to be 27? What if I start doing my tree from here? Am I going to get the same tree? I don't know. What's the cheapest edge next to this thing? 2. What's the next cheapest edge? 2. What's the next cheapest edge? What's the next cheapest edge? 4. What's the next cheapest edge? 5 is not adjacent to this, is it? What is the next cheapest edge? What if I take a different edge this time? I'm being kind of brave. What is the next cheapest thing I can do? And what is the cost of this going to be? 12 plus 4 is 16, 18. I hope to God this adds to the same thing. Does it add to the same thing? It should be, what is this? Sorry about this. 5 plus this, that's 12. 12 plus 2 is 14. 16. Why is this looking cheap to me? Is that right? What is the cost of this thing? That's 12 plus 7 is 19. That's 23. What does that mean? It meant I must have added up wrong the first time, right? 5 plus that's 12. 15. 15, and this is going to be 17. 21. Wait, 19. 19 plus 4 is 23. Does everybody agree that both of these are 23? Okay, fair enough. Okay, any questions about what Prim's algorithm does? Okay, how fast it does it and implement it, we'll talk about next time. What I want to do now is to argue why Prim's algorithm is correct. Okay? And it's not obvious that Prim's algorithm should be correct. The greedy algorithm for traveling salesmen was not correct. Why is Prim's algorithm going to be correct? Okay? We're going to do a proof by contradiction. Okay? What is a proof by contradiction? We're going to assume that Prim's algorithm is not correct. What does it mean if Prim's algorithm is not correct? It means there must be some graph where it doesn't give me the minimum cost spanning tree. Okay, fine. Show me this graph. If I start running Prim's algorithm on this graph, I'm going to start building up a tree. Does everybody agree? And if this Prim's algorithm is not correct on this graph, what is going to happen? I'm going to go start here, start adding edges, and everything is still possible. And at some point, the algorithm is going to say, eh. What does mean? It means so far what I built was in a minimum spanning tree, but this is where you went wrong. Recognize that if Prim's algorithm is incorrect, when I'm adding edges, there's going to be some point where what I have added, there's no possible way to make a minimum spanning tree from what I have added. Okay? And I'm going to say, oh, you're telling me that this edge I just added was the edge that broke the algorithm. That up till now everything was in a minimum spanning tree. But when I add this edge, there's no possible spanning tree that's as cheap as the minimum spanning tree you can get by taking blue plus this. So what am I going to say? I'll say, okay, show me what was that minimum spanning tree. And what's going to happen from that minimum spanning tree? Clearly it's going to use the blue edges. It's certainly not going to use that one. But somehow it's going to have to bring V into the minimum spanning, to connect with the rest of the tree. So there will be a path from Y out until it comes back into the spanning tree. This is the minimum spanning tree, you'll tell me. And I'll say, oh, that's nice. What happens if I add the edge that you said was bad to your minimum spanning tree? What happens if I add this edge to the spanning tree that you tell me is the